Good afternoon. Just looking into what we have concerning functions, and we will be looking into functions throughout the rest of the course. And going back to the set from section 1.3, and now for the graphs that we have to appear, we're looking to see if we have a function or not. And for the graph in number 16, remember, we're using the vertical line test, and a function is not going to have a vertical line to intersect its graph at 2 points at each x value. So for what we have here, so if I were to take a vertical line and run it through, and if you notice, we have for all the x values, you have the intersection at most 1 point. And so for this particular graph in number 16, okay, that is going to be a function. And for what we have in the case of the next item, okay, so we have a graph that looks almost like the letter S, and looking at applying the vertical line test, okay, and now there's part of the graph that would seem to suggest that we have a function until we get close to the y-axis. And if you notice, okay, say we have like on x is equal to 1, guess what? We have something like 1/1/2, as well as 1, -2.8, let's say, and like 1 and 3.3. And you have on the same x, you have more than 1 point of intersection between the graph and the vertical line. So in this case, right, that is not a function. And for what we have in the case of number 19, okay, so we have a vertical line test once again, and in the graph, okay, we have a horizontal line, okay, and if you run a vertical line through this, you have from end to end, okay, have just 1 point of intersection. So in this particular case, right, that is a function. For what we have in the case of number 20, applying the vertical line test, and guess what? The graph itself is a vertical line, and this one we have throughout, we have the x is equal to 2, and guess what? You have 2 vertical lines coming into contact, and guess what? We have an infinite number of points of intersection. So while a horizontal line will be a graph that represents a function, a vertical line is going to be anything but. Okay, so like x is equal to 2, okay, that is not a function. Again, for each x value, there should be only one corresponding y value. And here we have, for this graph, we have x equal to 2, and you have an infinite number of y values, say from like y all the way down to negative infinity and all the way up to approaching positive infinity. Now, in the case of what we have with the line segments in problem 22, and if we look at the vertical line test on this one, and most of it the graphs would seem to suggest that we have a function, but guess what? We have close points, let's say on x is equal to -1, and because these are official points, you got same x and different y values, and so this would not constitute a function. Okay, so again, for a function for each x value, there should be only one corresponding y value. And now, in looking at what we have regarding functions and expressions, and also evaluating functions for specified inputs, and we have in the same section, now we got a function f of x. Okay, that's a quadratic function where we have this set equal to x squared plus 3x. And for what we have in the case of determining function values and expressions, now we have in reference to f of x, now we have number 46. Now we're looking at f of -5. And again, f of x is a functional notation from what we otherwise say is y in the xy coordinate system. And with the x value at -5, okay, we're looking at what the corresponding value will be in y, okay, whenever, again, x is at -5. So with the input at -5, again, squaring the input, we have the square of -5. And we have plus 3 times the input, which is going to be 3 times -5. And the square of -5 is going to be at 25. And 3 times -5 is -15. And 25 minus 15 is equal to 10. Okay. So -5, 10 will be a point on the graph of y is equal to f of x is equal to x squared plus 3x. And we have, in referencing the same function, we have for number 51, okay, instead of numerical input, we're going to have a variable expression in a different letter. And in this case, we have the input at a plus 4. And looking at applying the f of x treatment upon setting x to a plus 4, so we have the square of x is going to be the square of a plus 4, and we have plus 3x, so this would be plus 3 times the quantity of a plus 4. And I'll just move this on down. Okay, so for a plus 4 squared, that is a plus 4 times itself. And if you were to envision FOILing out, okay, so you got your first product at a squared, outside product would be 4a, inside product is also at 4a, last product is 4 times 4, which would be 16. And then we have, with the terms that follow, upon distributing 3 over the quantity of a plus 4, we're going to have 3a plus 12. And consolidating the terms. Okay, so we have a squared is the only second degree term. And for the first order terms in a, we have 4a plus 4a is 8a. 8a in turn plus 3a becomes 11a. And with the constants, we have 16 and 12, and those will add up to 28. Okay, so we end up at a squared plus 11a plus 28. And we have among the functions, okay, along with f of x equal to x squared plus 3x, okay, we also have presented, okay, the reciprocal function where g of x is equal to 1 over x. And just a couple of items referencing this reciprocal function, okay, and we have for number 39, for 39, okay, so we have g of 3, okay, so in this one, okay, the only thing we had to do is substitute, and g of x becomes g of 3, and so we have 1 over x to become 1 over 3, and just with inputting 3 for x and the follow through. So we have a very short answer item whereupon we have g of 3 is equal to 1/3. And for what we have in the case number 41, okay, let's say if you have the input to not be at 3 but instead the reciprocal of 3. Well, guess what? We got the reciprocal function, so I'm taking the reciprocal of the input regardless of whether the input is a whole number or a fraction. So guess what? Right now we got 1 over 1/3. And in following through, upon simplifying, okay, so you got 1 divided by 1/3. And guess what? If I divide by a fraction, that'll be the same as multiplying by the fraction's reciprocal. And so this is going to end up at 3. Now, okay, so I have a quadratic function, an inverse function, and we have for h of x, okay, this is going to be a constant function. And basically this is going to be impervious to whatever input there is. And we have for h of x, okay, if you have, say, just changing over the input x to -7, well, guess what? There's no variable term or expression to work with on the right. It's, you just have the number 5. And whatever's put in for x is not going to do anything to budge 5 from where it stands. So h of -7 is equal to 5. And guess what? Even if you were to add another letter or another number, okay, and in the case of 50 we have h of x plus h. But guess what? There's no input variable, there's no mode of substituting, so there's nothing to make 5 undo itself. Okay, so regardless of what the input is, okay, we're going to have h of x, h of any input is going to stay at 5. We have also in the mix, okay, so we've had f of x, g of x, h of x, and now we have rounding out the quartet. Okay, we have the function k of x, and this is going to exist as a radical function, whereupon k of x is equal to the square root of x plus 1. And looking at the inputs, so we have in number 43, okay, so we have k of -5, and plugging in -5 for x, so I have -5 plus 1, and so this will be the square root of -4, and guess what? We had the square root of a negative, okay, and it's because of this, okay. Okay, we have no real solution. Now, you would have, okay, if this were anything else, okay, so you have a complex root so you have a complex number with 2i. But in chapter 1, we're no longer dealing with complex numbers. We're just sticking with real solutions where they exist. Okay, so for this section, okay, if we were looking at both real and complex solutions, okay, you would have 2i, but since we're looking at just finding real solutions, your result is going to be no real solution. Okay. Now, in the case of what we have with number 49, okay, this time we have with the variable expression, okay, so we're going from x to x plus h, and if k of the input is equal to the square root of the input plus 1, well, guess what? We have k of x leads to the square root of x plus 1. Well, here k of x plus h is going to lead to the square root of x plus h plus 1. And that is all there is in this one. All right. And again, so we have different capacities of looking at solving for functions in terms of numerical values as well as resulting expressions. Now, I'm just going back to what we have with sets of ordered pairs. And now the author has like the function given as f, but this is the implicit form of f of x. And we have in this array, okay, so we have sets of ordered pairs. Okay, whereupon we have 2, 3, 9, 7. Also we have 3, 4. And for the remaining ordered pair, okay, we have -1, 6. Right. And now regarding numbers 63 through 65. Okay, now for 63, we're looking at f of 8. Excuse me, f of 9. 64. Okay, we're looking for f of negative 1. And for 65, okay, so you have f of 3. Okay, so again, the numbers inside the parentheses will be in reference to the x values. And like f of 9, this is going to be the y value whenever x is at 7. And so for what we have here, okay, so looking for where x is 9, okay, so it's going to be this point. When x is 9, we have the y value to be equal to 7. So the y value whenever x is 7 is going to be y is equal to f of 9, which is going to be at 7. Now for number 64, okay, we're looking at the y value whenever x is at negative 1. So when x is negative 1, your y, or f of negative 1, is going to come out to 6. And in the case of f of 3, so again, your x value, not your y value, is at 3. So 3 appears twice. Once it's a y value, one is an x value. Now for f of 3, we're looking at the y value whenever x is 3, and so that is going to be at 4. Again, so you have 9, 7, negative 1, 6, as well as 3, 4. Now, just throw these two questions in, and this is sort of setting things in reverse, so to speak. And let's say that if you're posed the question, like, for what value of x is f of x equal to 6. Okay, so you have for what value of x is f of x equal to 6. And so for what we have in this instance, okay, so we got f of x is equal to 6. And again, f of x is just a functional notation for what we say is y. Okay, so you have y is equal to 6. And so for the missing value that we have here, so we're looking at what value x is y equal to 6. So for y is equal to 6, we got this ordered pair. So we have that x is equal to negative 1. Okay, so the value of x equal to negative 1 is going to be whereupon we had the y value to end up at 6. And just also throw in okay, and we have for what value of x is f of x equal to 4. So for what we have among the ordered pairs, okay, so where we have y is equal to 4, okay, your corresponding x value is going to be at 3. So again, we have f of x is equal to 4. Yeah, y is equal to 4, and again, corresponding x value is at 3. Now, the other day we were looking into several different examples of what constitutes the domain of a function. And we have with our functions, okay, beginning on page 100, or with number 100. Okay, now we're looking for domain. And for what we have in 100, okay, this is just a reminder of how to go about solving inequalities. Now we're looking at, in part A, okay, we're looking at where we have y of t is equal to the square root of 16 minus t. And again, we're looking at keeping this function as a real value or expression. And for the square root of 16 minus t, okay, now we have an even root radical. And because we have an even root radical, again, you cannot have the square root of a negative. So we had that 16 minus t cannot be negative. Okay, so you have a radical that's given in direct terms. Okay, now there's no fraction. Okay, and you can have the square root of 0, and you can also have 16 minus t to be a positive value. Okay, so for what we have here, okay, all right, so you have 16 minus t. Now it cannot be negative, but it can be 0 or positive. So if I were to set up an inequality concerning 16 minus t, okay, so it can be equal to 0, and when it is positive, we'll have it to be greater than 0. So the initial inequality we have at 16 minus t is greater than or equal to 0. And looking at solving for t, okay, if I isolate the t term, which we now have at negative t, and we have upon taking 16 away from both sides, okay, so I have negative t is greater than or equal to negative 16, and then looking at changing the signs, and it's going from negative to positive t. So I can either multiply or divide the terms by negative 1. And upon doing so, okay, so if I go and multiply or divide by negative, the direction of the inequality will flip. And so we have here, okay, so we have negative 1 times negative t is t, and t is going to be less than or equal to positive 16. All right, and so just looking at the domain and expressing in terms of an interval. Okay, so there's only one number that is involved in the inequality comparison, and that is the number 16. And with the nature of this, okay, so we got the equal sign. So 16 is included, and the rest of the values had to be less than. And so we're going to have a ray that is going to go continuously to the left. And you have continuous motion out toward negative infinity. Okay. And so we have, in the case of the domain, okay, so you have going from negative infinity, and a reminder, okay, infinities, positive and negative, remain in parentheses. So we have going past negative infinity out to and including the number 16, okay, which is going to be in the bracket. So this will be your domain solution for part A in problem 100. And for what we have in the case part B, okay, so just kind of shifting this over and swapping the order of the 16 and the t. Okay, now we have a function w of t is equal to the square root, not of 16 minus t, but t minus 16. And a lot of history repeating. Again, we have an even root radical function. So you have t minus 16, for the same reason, cannot be negative. And again, because it is an even root radical, and because it is given in direct terms, okay, it can still be 0. or positive. Okay, just like 16 minus t earlier from part A, you had the square root of 0 and the square root of a positive. So the inequality setup will have it where t minus 16 is greater than or equal to 0. And looking at isolating t, we have upon adding 16 to both ends. And guess what? We already have the inequality solution for t. Here we have that t is greater than or equal to 16. Okay, so we have 16 as the centerpiece number, so to speak. And so we have with the number 16, okay, so we have t is greater than or equal to 16. So we got for the equal to 16 part. Okay, so 16 has a point on it. And the rest of the values will be greater than 16. And so we have a ray that's going to go continuously to the right. And approach infinity. And so for what we have in the case of the domain, so I'm going from and including 16 on out to infinity. And now, okay, so with the functions y of t and w of t, okay, both of these were radical functions, and again, the order of 16 and t were interchanged. Now, for our function z of t, okay, this is going to play a dual role as both radical and a rational function. And now we're going back to the square root of 16 minus c, but this time with z of t, okay, we have the reciprocal of the square root of this difference expression. So now we got z of t, we have 1 over the square root of 16 minus t. And again, just some items again to consider. Okay, we got a square root. Okay, and so 16 minus t cannot be negative. And if you notice, because of the location, since 16 minus t is in the denominator of a rational expression, and because you cannot divide by 0 in the real number system, so we have that you cannot have the square root of 0 here. So we have 16 minus t cannot be 0. So it cannot be negative, cannot be 0. So that leaves only one possibility here. Okay, and you can have a positive number in the denominator and the square root of a positive number. So 16 minus t can only be positive. And just taking what we have for the restriction here. Okay, so you have 16 minus t. Okay, there's no longer equal to 0. Positive means it's greater than 0, so this is going to be our inequality setup. And looking at solving for t. Okay, so you have from 16 minus t is greater than 0. So if I look at isolating negative t, and we have upon taking 16 away from both ends, so we have negative t is greater than negative 16. And just changing the signs once again at both ends. Again, so you're just going to go from the negatives to the positives, and Upon doing so, the direction of the inequality changes. And so we will have in the rewrite, we're going to have that t is less than 16. And so just visualizing. So again, we have 16 to work around. Now 16 is not included. Okay, so this is indicated by, once again, an open circle. And again, everything is less than. So we'll have a ray that's going to go out to the left. Approaching negative infinity. And so we have with the activity, okay, or what is allowable for t, we have, once again, for the domain, we will have the set of all values t, okay, such that we have t to be between negative infinity and, but not including, 16. Okay, so the result here is going to be an open interval. Okay, now, so we have radical functions throughout, and the last one presented in reciprocal terms. Now, for what we have, just doing a little bit of a change up in terms of the type of function, and we have for number 104, I had mentioned just part C, but we can look at parts A and B also. And for part A, okay, we have a function r of x, and that is equal to x squared minus 4x minus 12. And in this one, okay, so I don't have an even root radical, I do not have a fraction, I just have a quadratic function. I have x squared minus 4x minus 12. So for x, for both x squared and the x and negative 4x, I can plug in any value from the real number system and still have a defined expression. Okay, so in this one, we don't have any restrictions, meaning that x could be a 0, it could be a positive, it could be a negative. And since r of x has no restrictions, okay, we can say that the domain is going to be the set of all real numbers. Again, that's symbolized by parentheses surrounding negative and positive infinity. And for what we have in the case of part B, okay, now we have the function s of x is looking at taking this same quadratic expression and dividing by x plus 1. So here we have for s of x, we have x squared minus 4x minus 12. And then we have all over x plus 1. Right, so we got a fraction, and for s of x to be defined, okay, we cannot have a 0 denominator. And in this case, we have the denominator at x plus 1, and if that cannot be 0, we're going to have the x cannot be negative 1. And so upon looking at what we have now, okay, so you have only one excluded value. You almost had the whole real number system, and you do except for the number 1. So for the activity, we'll have two separate interval sections. One is going to be where we have x is less than negative 1, and the other is going to be where we have that x is greater than negative 1. So you have the ray that's going to go continuously to the right in the direction of positive infinity. So for the domain, you have one exclusion, and from this exclusion, we're going to have two separate interval sections. And so here we have, for those values on the lower end, we have between negative infinity and but not including -1. So you have parentheses. And then for the other part, you have bypassing -1. And for the values of x greater than -1, you have parentheses around -1 and positive infinity. And so that would be the domain and interval notation for what we have in the function s of x equals x squared minus 4x minus 12 all over x plus 1. And for t of x, this is just taking the reciprocal of s of x, where x plus 1 is at the top, and the trinomial x squared minus 4x minus 12 is going to reside at the bottom. Again, have just a fraction, no even root radical, and the potential restrictions will come from disallowing the denominator, in this case x squared minus 4x minus 12, from being 0. Okay, so you have x squared minus 4x minus 12. If I factor, we have x plus 2 and x minus 6. And to keep this whole expression from equaling 0, we cannot have these factors to be equal to 0 either. So for x plus 2, if this cannot be 0, well, x cannot be -2. And if x minus 6 cannot be equal to 0, well, we have that x cannot be equal to 6. Okay, so we have two exclusions from the domain. And what's going to happen here? Notice before in part B there was one exclusion, and the domain of s of x had two separate interval sections. Well, guess what? We're adding an exclusion, and we'll also be adding a subinterval section. So going from 2 subintervals to 3. And so we have for the numbers of interest. Okay, so you have -2 and 6. Again, both of these numbers are left out. You have open circles to indicate the exclusions. And so for what is going to be allowed will be those values in between -2 and 6. And also we have those values greater than 6, and also those that will be less than -2. So getting this other one in. Okay. For the domain, okay, we have at the lowest end, okay, so you have going from -infinity, approaching but not including -2. And then we have for the middle strip, this line segment, so you have between but not including -2 and 6, so we still maintain the use of parentheses. And for the rest, we have those values of x, okay, which will be greater than 6. So you got 3 subintervals, and all of these will have the interval notation grouping symbols to be exclusively parentheses. All right, and again, the topic of domain, okay, this will be going on continually, maybe not continuously, but continually, as we proceed from one section to the next. All right, now we had left off, okay, with concepts concerning linear equations in two variables, and just kind of picking up where we had left off. And where we left off was in the realm of working with slope. And we're going to sort of continue with this, but start looking into equations officially. Again, just to restate, again, we had slope, and the slope m is equal to the change in y with respect to change in x. Here we have y of 2 minus y of 1 all over x of 2 minus x of 1, and again to avoid a zero-valued denominator. X of 1 and x of 2 cannot be equal to each other. Now, involving slope, okay, there is one type of equation, and this is going to be referred to as the point slope equation of a line. And for the point slope equation of a line, or some might call it the point slope form of a linear equation, same thing. And we have now the point slope equation of a line with slope m and that runs through a point. Here we have x1, y1 is going to be. Now we normally say x before we do y. Since alphabetically x comes before y. But in the case of the point slope equation, you're going to see this with y terms at the front. And here we're going to have y minus y1 is equal to the slope m times the quantity of x minus x of 1. So this is going to be the point slope form of a linear equation. Now we have, again, you have the coordinates x1, y1, so you're going to have y minus y1 is equal to the slope m times the quantity of x minus x of 1. And if I were to isolate this particular y, okay, so we have, in the case of isolating y, okay, this is going to lead to the next type of equation. And it's going to be what is regarded as the slope-intercept form of a linear equation. Or the slope-intercept equation of a line. Okay, so by getting this y by itself, okay, we'll have the following to arise. Okay, so we had that y is equal to m times x plus b. And regarding the characters, okay, we'll have again, so m is going to be the slope. Also, when we're talking about the slope-intercept equation now, the slope is m. Now the intercept is going to be in reference to the y-intercept. And this is where the constant b comes in. And there are two ways that you could express the y-intercept. I know that Alex likes to put it in terms like y is equal to b. But another way would be just like what point on the y-axis would the line representing this equation touch or cross. And so that ordered pair would be 0b. So whenever x is 0, your y is equal to that constant that represents the intercept. Okay, so again, m is the slope, and the y-intercept, you can say either y is equal to b, or just specify the ordered pair on the y-axis, which is going to be 0b. And looking at tying together these types of equations, and we could say that for what we have among examples. Okay, let's say that if you have to determine the slope-intercept equation and say we have given, we'll have a case of where the slope is provided. So you have that m is equal to 5, and we'll have the point through which the line passes. We'll say the location is going to be -1, -2. All right. So just for the backdrop, okay, so in determining the slope-intercept equation, so the object is going to be to get y by itself. Now, in terms of the point-slope equation setup, again, we have y minus y1 is equal to the slope m times the quantity of x minus x01. So looking at y minus y01, okay, so we have y minus -2. For the slope m is going to be at 5. And we have times the quantity of x minus x01, whereupon x01 is at -1. And undoing the double negatives, okay, so you have y plus 2 is equal to 5 times the quantity of x plus 1. Okay, now let me pause right here. Okay, so this case with your y expression on one side and what we have in x on the other, at this stage, okay, this is going to be the point-slope equation. Now, okay, so the point-slope equation, okay, this is essentially at the stage where you have the y expression where y is not isolated, and also you have your x terms where you don't have the breakup of the parentheses right yet. And now for the crossover to getting to the slope-intercept equation. Okay, so I'm going to distribute 5 over the quantity of x plus 1. So this is going to be 5x plus 5. And then we have getting y by itself. So if I take 2 away from both ends, okay, so we had that y is equal to 5x plus 3. And so this is going to be our slope-intercept equation. And just some things to mention. Okay, so the slope is at 5, and that 3 means that the y-intercept, okay, is going to be the location where the graph is going to cross the y-axis at y is equal to 3. So y equals 3 is going to be the y-intercept. Again, the slope is going to be at 5. And again, you can sort of test what we have out. Okay, so -1, -2 will be a point on the graph of this function. And you can test, like say if I have y is at -2 whenever x is at -1, you should have both sides to be equal to each other upon substituting. So left-hand side y is going to be -2, and we want the right-hand side to be as well. So with x at -1, we have 5 times -1 is -5, and -5 plus 3 is also -2. So this will check out. Now, as another instance of determining the slope-intercept equation, and we'll say that we have the slope, we'll say is -4, and we'll say that the ordered pair of the point through which the line is going to pass, we'll say this is going to be at 2, 6. And so just for the backdrop here, okay, so you have y minus y01 is equal to the slope m times the quantity of x minus x01. So just filling in, so you have your y01 is at 6, x01 is at 2. So for y minus y01, okay, so that's going to be y minus 6. For the slope m, okay, we have at -4, times the quantity of x minus 2. And this is going to be the point slope equation. And looking at getting y by itself. Okay, so going ahead and distributing on the right hand side. -4 over the quantity of x minus 2. Okay, so this will be -4x plus 8. And in terms of getting y by itself, okay, so if I add 6 to both ends, okay, so we're going to have y is equal to -4x, and 8 plus 6 is 14, so you have y is equal to -4x plus 14, and that is going to be the slope-intercept equation outcome. And we can check once again for the consistency. Okay, so you got the slope as stated at -4, and for 2, 6, 2 for x, 6 for y. So left-hand side of the equation is 6, and we want the right-hand side to be as well. And with x at 2, we've got -4 times 2 is -8, and -8 plus 14 also rests at 6. And now, just some items and looking at the determination of the slope-intercept equation. And let's say that okay, so if we're looking at determining the slope-intercept equation of the following. Let's say we have an equation that is in standard form where we have the x and the y terms on the same side. And let's say we have 2x plus 3y is equal to 12. And we'll say also for the next item we'll have the slope given, whereupon we have the slope is equal to -3, and the point through which the line passes will be at 210. So one that has a bit of an added twist. Let's say that instead of the slope being given, will have 2 points through which the line passes. And so I have the line to pass through -1, -1, and 311. So for the next few moments, okay, let's see what the slope-intercept equation will be for each of these situations. I'm again talking about where we have y is equal to mx plus b. Okay, if you're still working on these, that's quite all right. Just looking at finding out what the slope-intercept equations are going to be corresponding to the given situations. We have in the first, okay, we have two variable expression, okay, set equal to a constant. So we have x and y on the same side of the equation. I'm looking at rewriting 2x plus 3y equals 12 in terms of just y equals. And so to get this into the slope-intercept form, I can undo the presence of 2x on the left. So I can just take 2x away from the left-hand side. And so I have by itself, I have right now 3y is equal to, okay, and you could start out saying 12 minus 2x. But just to get the variable term at the front of the constant, we'll just say we have -2x plus 12. And then writing in terms of y, okay, if we divide everything out by 3, okay, so arriving at the slope-intercept equation, okay, so the left-hand side is going to be at y, and we have is equal to, okay, so your m value is going to be the fraction -2/3. So we got y is equal to -2/3 of x, and for the b value, have 12/3, and that reduces to 4. So the slope-intercept equation for what we have in case number 1 is y is equal to -2/3 of x plus 4. Now, in looking at what we have in the second case, right, so we have the slope given and a point through which the line passes also provided, and utilizing the point slope equation backdrop as a pathway to getting to the slope-intercept. Okay, so we got y minus y of 1, okay, and so we can specifically translate that to y minus 10 is equal to m, which we have at -3, and we have times quantity of x minus x of 1, which will be that of x minus 2. Okay. So the only thing I have done is just a substitute for y of 1, m, and x of 1. So I got the point slope equation, and getting this in line with the slope-intercept equation. Okay, so we have upon distributing -3 over the binomial x minus 2, so we have -3x plus 6, and getting y by itself upon adding 10 to both sides. And so it's going to follow that y is equal to -3x plus 16. So you had the slope at -3, and I can check for consistency. So y is at 10, left-hand side of the equation is at 10, and for x at 2, -3 times 2 is -6 plus 16 is also going to yield 10, which is what we're going to have on the right-hand side. So 10 is equal to 10, and so that is going to check out. Now, for what we have in in the third case. All right, so we have 2 points through which the line passes at -1, -1, and 3, 11. And now, for what we have here, we got these 2 points given, and to get to so much a slope, we have to determine the slope of the line that passes through these 2 points. And we'll go ahead and identify the x's and y's. And since we have -1, -1 given first, we'll just designate that for x1, y1, and have 311 to be representing x2, y2. But if I had it the other way around, like if 311 had been given first and -1, -1 subsequently, it's still going to be the same slope. And looking for the slope once again, so y2 minus y1 all over x2 minus x1. So you got y2 is at 11, y1 is at -1, x2 minus x1. So we have 3 minus -1, and subtractions of negatives will revert to addition. Okay, so the total vertical change we have at 12, and the total horizontal change is going to be at 4. And breaking it down in terms of proportions, like a 12:4 ratio reduces to a 3:1 ratio. So the slope is going to be equal to 3. And for the point slope equation setup, you can choose either -1, -1, or 311 for x1, y1, in the point slope equation. Again, either ordered pair will work, and I say that perhaps the more popular choice, and that is to not work with negatives any more than necessary. We could go with 311. And so just creating a backdrop, say y minus y1 is equal to the slope m times the quantity of x minus x01, and just looking at what we have for the numbers. Okay, so we got 11, okay, that will represent y01, and we have, in the case of m, okay, so you have m, okay, you had the slope to be at 3, and also for the 3 and the 311, okay, that was me in reference to x of 1. Okay. All right, so just filling in the numbers. Okay, so we have y minus 11 is equal to 3 times, okay, the quantity of x minus 3. Okay, so this is our point slope equation. Now for the slope intercept, if we follow through, okay, so we have y minus 11 is equal to 3x minus 9 and getting y by itself upon adding 11 to both sides. And it's going to turn out that y is equal to 3x plus 2. And so this will be the slope-intercept equation. And you can check both ordered pairs. So if y is at 11 when x is at 3, we've got 11 on the right and 11 on the left, and you should have it on the right as well. And with x at 3, 3 times 3 is 9, 9 plus 2 is 11, 11 is equal to 11. And had I worked with -1, -1, it should still work out in this fashion too. So if y is -1, we want the right hand side of the equation to also be -1. And with x at -1, we got 3 times -1 is -3. And in turn, -3 plus 2 is -1, so we have -1s on both sides. So I could have chosen -1, -1 to work in the point slope setup as well, and it worked still for both ordered pairs. All right, now in the crossover, just right quickly to relations of linear types. Just want to mention, okay, for parallel and perpendicular lines, and for what we have concerning parallel and perpendicular lines, okay, just kind of a quick run through. For parallel lines, okay, parallel lines, okay, those are going to be distinct. Yeah, distinct non-vertical lines. That have the exact same slope and will never intersect. And just examples of lines that run parallel to each other. Okay, so we have as first case. All right, so if I have, let's say that y is equal to 4/3 of x minus 2, and we had that y is equal to 4/3 of x plus 7. Okay, so you have almost the same expression, except you have different y-intercepts. First one with -2, the second with 7. But now the main criterion for parallel lines, okay, is going to have the same slope. In this case, which is going to be the x-term coefficient. Okay, so you have the same slope at 4/3, and with the same slope and with the lines being different from each other, they're not going to come into contact, and so we can say that the lines are parallel. And we have as second case here, okay, if we got that y is equal to 7x minus 3, and y is equal to 7x plus 4. Again, we have distinct lines, and both of these are given in slope-intercept form, so right away we can tell that we're going to have the same slope, which is going to be at 7. And again, the lines are going to be parallel to each other. Again, use shorthand notation, what looks like a sideways 11. And in the case of perpendicular lines, okay, those are going to be non-vertical lines. That will meet at a 90-degree angle or a right angle. and in terms of how they're going to meet, or how they meet at a 90-degree angle, their slopes are going to be opposite sine reciprocals of each other. It's a little bit wordy, but by opposite sine reciprocals, this is saying, in other words, that the product of the slopes is going to be -1. And just drawing out what we have here. Okay. For examples of perpendicular lines. So you have like y is equal to 4/3 of x minus 2. And we'll say they have with y, I'm just going to kind of maintain the coefficients. Okay, now to make our x term to represent opposite sine reciprocal of 3/4, that is going to be -3/4 of x. So we have 4/3 times -3/4 is going to be equal to -1, and so these lines are going to be perpendicular, and the shorthand for perpendicular is going to be an upside down T. And let me just for this last one here, okay, so we got y is equal to 7x minus 3. And if I take the opposite sine reciprocal of 7, this is going to be a -1/7. So -1/7. Let's say we have of x plus 4. Again, yeah, with the slopes, we got 7 times -1/7. So that's -7/7, which is also -1. And so these lines are also perpendicular.